Hi, I am Teacher Daisy. Now, let's learn Form 4 Mathematics Chapter 5, Network and Graph Theory. In this chapter, you will learn 5.1 Network. 5.1 Network, relationship between a network and a graph. A graph is used to represent data, consisting of discrete objects, and to show the relationship between these objects. In a simple graphical manner, a graph is interpreted as a series of dots, which are either linked or not linked to one another by lines. Each dot is known as a vertex, dot or node, and the line joining two vertices is known as an edge, arc or link. A graph is usually used to represent a certain network. A network is part of graph, with the vertices and edges having their own characteristics. The structure of network data has a many-to-many relation. Examples of graphs that involve networks: land transport network, vertex, regions, towns, cities or certain buildings that are linked. Edge, roads, highways, or railway lines. Social network, vertex, individuals, groups, or organizations. Edge, types of relationships such as friends, colleagues, or families. A graph is denoted by a set of ordered pairs, G equals V, E, where V is the set of dots, or vertices, V equals V1, V2, V3, Vn. E is the set of edges, or links, linking each pair of vertices. E equals E1, E2, E3, En. E equals A1, B1, A2, B2, An, Bn. A and B are pairs of vertices. The degree, d, is the number of edges that connect two vertices. The sum of degrees of a graph is twice the number of edges. For instance, V equals 1, 2, 3, 4, 5, 6, E equals 1, 2, 1, 5, 2, 3, 2, 5, 3, 4, 4, 5, 4, 6. A simple graph has no loops and no multiple edges. The sum of degrees of the graph is twice the number of edges. Example: based on the simple graph given, determine A, V and NV, B, E and NE, C, sum of degrees. Solution: A, V equals 1, 2, 3, 4, 5, 6, and V equals 6. B, E equals 1, 2, 1, 5, 2, 3, 2, 4, 3, 4, 4, 5, 5, 6, and E equals 7. C, sum of degrees, sigma dB equals 2 times E, equals 2 times 7, equals 14. Example: state the number of vertices, edges, and the sum of degrees for the following simple graphs. Solution: A, number of vertices equals 7, number of edges equals 7. Sum of degrees equals 2 times number of edges, equals 2 times 7, equals 14. B, number of vertices equals 7, number of edges equals 9. Sum of degrees equals 2 times number of edges, equals 2 times 9, equals 18. Meaning of multiple edges and loops of the graph. Multiple edges involve two vertices. The vertices are connected by more than one edge. The sum of degrees is twice the number of edges. Loops involve one vertex. The edge is in the form of an arc that starts and ends at the same vertex. Each loop adds 2 to the degree. Example: the diagram shows a graph with a loop and multiple edges. State: A, V and NV, B, E and NE, C, sum of degrees. Solution: A, V equals P, Q, R, S, T, U, and V equals 6. B, E equals PQ, PU, PU, QR, QU, RS, RT, SS, ST, TU, N, E, equals 10. C, sum of degrees, equals 20. Degree of vertex P, equals 3. Degree of vertex Q, equals 3. Degree of vertex R, equals 3. Degree of vertex S, equals 4. Degree of vertex T, equals 3. Degree of vertex U, equals 4. Example: draw a simple graph based on the given information. A, V equals 1, 2, 3, 4, 5. E equals 1, 2, 1, 4, 1, 5, 2, 3, 2, 4, 3, 4. B, V equals P, Q, R, S, T, U. E equals PU, PT, QT, QS, RS, RU. Example: draw a graph with multiple edges and loops, based on the given information. A, V equals P, Q, R, S. E equals PP, PQ, PS, QS, QS, QR, SR, RR. B, V equals 1, 2, 3, 4, 5, 6, 7. E equals 1, 6, 1, 6, 2, 7, 2, 7, 5, 7, 5, 7, 3, 4, 3, 4, 1, 7, 6, 7, 3, 7, 4, 7. Example: determine whether a graph, with the following degrees of vertices, can be drawn. A, 3, 2, 2, 1, 3, B, 2, 1, 1, 3, 3, 2. Solution: A, sum of degrees, equals 3 plus 2, plus 2, plus 1, plus 3, equals 11. The graph cannot be drawn, because the sum of degrees is odd. B, sum of degrees, equals 2 plus 1 plus 1 plus 3 plus 3 plus 2, equals 12. The graph can be drawn, because the sum of the degrees is even. Difference between a directed graph and an undirected graph. A directed graph is a graph in which a direction is assigned to the edge, connecting two vertices. Directed graphs are usually used to represent the flow of a certain process. For instance, road maps, airlines networks, electrical circuits, computer networks, organization charts. Simple directed graph. Based on the directions of the arrows, it can be seen that A, for edge AB, A is the initial vertex, and B is the terminal vertex. B, for edge CB, C is the initial vertex, and B is the terminal vertex. C, all vertices are connected in one direction only. Directed graph with a loop and multiple edges. Based on the directions of the arrows, it can be seen that A, E4 equals P, R. P is the initial vertex, and R is the terminal vertex. B, E5 equals R, P. R is the initial vertex, and P is the terminal vertex. C, E2 equals Q, Q. Q is the initial vertex, and the terminal vertex, because E2 is a loop. An undirected graph is a simple graph or graph with loops and multiple edges drawn, without any direction being assigned. Simple graph. Undirected graph. V equals A, B, C, D. E equals a B, a C, BC, CD. The order of the vertices written is not important. Both pairs of vertices, AB and BA, represent the edge AB. D equals 2, dB equals 2, dC equals 3, dt equals 1. Sigma dV equals 8. Directed graph. V equals A, B, C, D. E equals BA, CA, BC, DC. The order of the vertices are written according to the direction of the edge. BA and AB represent different edges. D in A equals 2, and D out A equals 0, thus, D equals 2 plus 0, D equals 2, D in A means the number of edges going into vertex A. D out A means the number of edges coming out from vertex A. D in B equals 0, D out B equals 2, D in C equals 2, D out C equals 1, D in D equals 0, D out D equals 1. Sigma dV equals 8. Graph with loops and multiple edges. Undirected graph. V equals P, Q, R, S, T. E equals PT, PQ, QR, QR, QS, ST, TT. dP equals 2. dQ equals 4. dr equals 2. ds equals 2. dt equals 4. Sigma dV equals 14. Directed graph. V equals P, Q, R, S, T. E equals PQ, QR, RQ, SQ, TS, TT, TP. D in P equals 1. D out P equals 1. D in Q equals 3. D out Q equals 1. D in R equals 1. D out R equals 1. D in S equals 1. D out S equals 1. D in T equals 1. D out T equals 3. Sigma dV equals 14. Differences between weighted graphs and unweighted graphs. The edges are labeled with numbers called weights. Weighted graph, unweighted graph, type of graph, directed graph and undirected graph. Directed graph and undirected graph. Edge, associated with a value or a weight. Not associated with a value or a weight. Example: the edge represents distance between two cities, traveling time, the current in an electrical circuit, cost. The edge relates information like job hierarchy in an organization chart, flow chart, tree map, bubble map. Example: draw a directed graph based on the given information. A, V equals P, Q, R, S, T, U. E equals PQ, PR, RQ, SR, SQ, ST. A, vertex pair, direction. PQ, P to Q, PR, P to R, RQ, R to Q, SR, S to R, SQ, S to Q, ST, S to T. B, there is a loop at vertex Q, and RS is a multiple edge, such that D in P equals 1, D out P equals 1, D in Q equals 3, D out Q equals 2, D in R equals 0, D out R equals 3, D in S equals 3, D out S equals 1. Total number of vertices equals 4. RS, a multiple edge, a loop at vertex Q. Complete the graph, based on the number of edges, going into and coming out from each vertex. Example: the diagram shows one-way paths that Israel can choose for his running practice. Vertex V1 is the starting position and vertex V5 is the ending position, before he goes home. Determine A, the shortest distance from V1 to V5. B. The longest distance from V1 to V5. C. The vertices that must be passed through, if the distance of the one-way run is between 1.4 kilometers and 2.1 kilometers. Solution: A. Shortest distance equals V1 to V2 to V5 equals 600 plus 500 meters equals 1,100 meters equals 1.1 kilometers. B. Longest distance equals V1 to V2 to V3 to V4 to V5 equals 600 plus 900 plus 500 plus 500 meters equals 2,500 meters equals 2.5 kilometers. C. V1, V3, V4, V5, and V1, V2, V4, V5. Identify and draw subgraphs and trees. A subgraph is part of a graph, or the whole graph redrawn, without changing the original positions of the vertices and edges. A graph H is known as the subgraph of G if A. The vertex set of graph H is a subset of the vertex set of graph G, that is VH, subset VG. B. The edge set of graph H is a subset of the edge set of graph G, that is EH, subset EG. C. The vertex pairs of the edges of graph H are the same as the edges of graph G. Example: determine whether diagram 1, diagram 2, diagram 3, and diagram 4 are the subgraphs of graph G. Solution: diagram 1, yes, because the vertex pair for edge E5 is the same. E5 is the subset of E1, E2, E3, E4, E5, and PS is the subset of P, Q, R, S. Diagram 2, no, because the position of loop E2 is not on vertex Q. Diagram 3, no, because the edge connecting vertex P and vertex S is not E3. Diagram 4, no, because the loop and the edge connecting vertex Q and vertex R are wrong. A tree of a graph is a subgraph of the graph, with the following properties: A. A simple graph without loops and multiple edges. B. All the vertices are connected, and each pair of vertices is connected by only one edge. C. Number of edges equals number of vertices minus 1. Number of vertices equals n. Number of edges equals n minus 1. This diagram is a tree because all the vertices are connected. Every pair of vertices is connected by an edge only. There are no loops or multiple edges. 5 vertices, 4 edges. This diagram is not a tree because vertex B and vertex E can be connected in 2 ways. 1. B to E, 2. B to C to D to E, 5 vertices, 5 edges. Example: determine whether each of the following graphs is a tree. Justify your answer. Solution: A. Not a tree. 6 vertices, 7 edges. Each pair of vertices can be connected in various ways. B. A tree. 6 vertices, 5 edges. Each pair of vertices is connected by one edge. C. A tree. 6 vertices, 5 edges. Each pair of vertices is connected by one edge. D. Not a tree. 6 vertices, 4 edges. Vertex R and vertex T are not connected to the other vertices. Example: draw a tree for the following information given. A. 6 vertices, B. 8 vertices. Solution: A. 6 vertices, 5 edges. B. 8 vertices, 7 edges. Example: draw 2 trees based on the graphs given below. Solution: A. 5 vertices. In order to change to a tree, should have 5 minus 1, 4 edges. The original diagram has 7 edges, which exceed by 3. B. 6 vertices. In order to change to a tree, should have 6 minus 1, 5 edges. The original diagram has 8 edges, which exceed by 3. Example: the following diagram shows an undirected weighted graph. Draw a tree with a minimum total weight. Solution: Step 1, 5 vertices, 7 edges, 3 edges to be removed. Remove edges with the greatest weights, PQ, QR, PT. The graph above is not a tree, because vertex P is not connected to the other vertices. 3 edges, RS, ST and RT, connect 3 vertices only. Step 2, between the weights 19 and 25, keep weight 19, because its weight is smaller. Between the weights 12, 14, and 17, remove weight 17. The graph obtained is a tree. Minimum total weight of the tree equals 10 plus 12, plus 14, plus 19 equals 55. Represent information in the form of networks. A network is a type of unique graph, and can be used to represent overlapping and intersecting information. Networks are widely used in almost every area of our daily lives. A network that is drawn and displayed in graphic forms enables the interrelationships between various information or data structures. To be understood easily, networks can be drawn as directed weighted graph or directed unweighted graph, undirected weighted graph, or undirected unweighted graph. Transportation networks can be shown as weighted graphs and unweighted graphs. The weights can represent the distance, traveling time, or cost of the journey. The navigation system in the weighted transportation networks is the GPS, Global Positioning System. For instance, the train transit network in Kuala Lumpur Central, KL Central. This undirected graph is an example of transportation networks, with the vertices representing names of stations that are connected and the edges representing the types of trains. Social networks. Social networks are used in areas like job opportunities, business opportunities, socializing, family relationships, education, social media, and connecting with communities around the world. Example: the table below shows the data of 6 pupils, and the games that they like. Represent the information in the form of a network. Let the vertices represent types of games, and the edges represent the pupils' names. Solve problems involving networks. Example: the map above shows the domestic flight routes of a private airline in Malaysia. A. Mr. Joshua works in Kuala Lumpur. He wants to visit his family in Kota Kinabalu. State the best route Mr. Joshua can choose. The direct flight from Kuala Lumpur to Kota Kinabalu. B. What are the advantages of direct flight and disadvantages of transit from Kuala Lumpur to Kota Kinabalu? B. The direct flight from Kuala Lumpur to Kota Kinabalu saves time and cost. The flight from Kuala Lumpur to Kota Kinabalu with transit takes a longer time, and most probably the cost of the journey is also higher. The concept map of Form 4 Chapter 5 Mathematics is as below.
If you find this video helpful, don't forget to like, share and subscribe our channel. And if you got any question can comment below. Thanks for watching.